And finally, we have this idea of the order. Order is something that's used to compare how the concentration affects the rate of the reaction. All right, we all good with that slide? Well, let's take a look at what these things look like. If you're given concentration versus rate, I had mentioned this in the previous slide, the differential rate law is concentration versus rate, then you can figure out what the differential rate law. This is what a differential rate law looks like. Rate equals K, some constant K, I'll talk about that in a moment, times the reactant concentration to the n power. And the n power up there represents the order. And my son just sits there and laughs at you without helping.
Yeah.
Every rate law, whether it's a differential rate law or an integrated, now we haven't seen an integrated rate law yet, we will, is always going to have this K in it somewhere. The K is called the rate constant, and it does represent a constant number. It's a number that's constant to a specific reaction at a certain temperature. So there's not just one number that we always plug in for K. K depends on what the reaction is. The higher the K, the faster the reaction is. So K is specific to the reaction. If you increase the temperature, it will cause K to increase because the particles are moving faster, they collide more frequently, and the reaction goes faster. But every one of these rate laws is going to have a K in it somewhere to kind of hook together all the other things that are changing. Again, the n value up there is called the order. It determines, or it's determined by an experiment. We're going to take an example of a chemical reaction. This is a decomposition reaction at 205. Remember, and by the way, I didn't mention this yet, the brackets right there, you've seen brackets several times from the first slide. The brackets represent concentration, molarity. So we run an experiment and we find that this is a first order reaction. Now, that will be more obvious as we go along. There's nothing that we've learned so far that would lead us to know anything about how we find the order, but we will. In fact, we're going to do a lab on Monday where we're going to have to find the order of a reaction. Now, don't write what's at the top because it's just carried over from the previous slide. We've got this chemical equation, experiment shows it's the first order. What first order means is this, that the rate, which is the change in the reactant over time, that's what the rate is defined as, is equal to some constant K times the reactant concentration to the first power. That's what first order means, is it's the exponent on the concentration is a 1. Yeah, it looks like a differential equation, doesn't it?
Yeah. I guess I need to
So this is the differential rate law. You could just replace this word, this expression with the word rate, because the rate is the change in the reactant over time. So that's equal to the rate constant times the N2O5 to the first power. And we're going to take that relationship, the way it's written, and express this change over time as a differential equation using instantaneous changes. I'm going to rearrange this thing and integrate. And rearranging it, I want to put all the N2O5 terms on one side and the non-N2O5 terms on the other side. So that's going to look like this. I'm going to take this N2O5 concentration divided on both sides. So 1 over concentration N2O5. And I'm going to keep this term because it's got the N2O5 term in it as well. That T term, I'm going to move it over to the other side. So, yeah, and that negative, we lost a negative sign in here, so I'm going to move the negative sign over to the other with the dt. So negative K dt. You don't have to do this math, so if you've never seen it before, don't start to squirm in your seat. If you have seen it before and you still don't like it, don't worry. This is the only time you're going to see integration happen at all. This whole chapter, the whole year. Right now? You haven't done integrals yet then, have you?
No,
We did.
Oh, have you? Okay. So if we take this expression and integrate over a time interval, so from 0 to t, do that on both sides. What is the integral of 1 over concentration of N2O5? Have you not learned that one? Matthew, you know it. It's natural log, right. Natural log of N2O5. Now, when you have it over a time interval, it would be the natural log at time t minus the natural log 1 over, the natural log at time 0. That's what the left side evaluates to. On the right side, the k is a constant, so you can pull that out of the integral, and what's just the integral of dt? It's just t. So that equals negative kt. It would be a subtraction of time t minus time 0, but the time 0 is 0, so I just leave it out. So we have this. And what does this give us? If I take this term right here, when I have a 0 subscript there, that means the initial concentration of N2O5. The initial concentration is whatever I started with of that. That number is going to wind up being a constant value because every trial, whatever your initial concentration of N2O5 is, that's what it was. And no matter what happens the rest of the way, you know what the initial concentration was. So this term, the constant, I'm going to move over to the other side. So that it's being subtracted on the left, I'm just going to add it to both sides. So on the next slide, you're going to see the same equation but I have moved this constant number over to the right. So the natural log of N205, I've taken out the little subscript t too. It just means at some time t equals negative kt. That negative sign's got to be there, plus natural log of the initial concentration. So what does this do for us? What did we just do? Well, it turns out that as the reaction proceeds, time is moving on, and the concentration of N205 is changing. The K is the rate constant. It's a constant number. The initial concentration is a constant number. So what does that look like? Variable equals constant times variable plus constant. Matthew? The slope-intercept form of a straight line. It winds up, if it's first order, and remember the whole premise was that this was a first order reaction. If it's first order, that means that we're plotting this term versus time, and it winds up being a straight line. With the slope equal to negative k. I should have said negative k is the slope. That really is mathematically correct. It's negative k. The k itself should be a positive number. This does give us a negative slope. The slope's like that, but we would have to just make it positive.
No, it's
Yeah. We'll have to calculate it.
K, right?
Yeah.
During the last one.
Yes. Now the y-intercept is this constant value right here, y equals mx plus b. And I've got a term in, or an expression in red here. This is really what it comes down to. If you have a set of data of concentration versus time, and you take the natural log of all the concentrations, plot it versus time, only if it's first order will you get a straight line for that plot. That's how we test to see whether the order is first or second or whatever order. If the natural log versus time gives us a straight line, that means it was first order. Kind of a weird way to check for what order. That's what we have to do. Yes, sir.
So then would that mean if it's a quadratic function, would that be a second order? And then cubic would be
No, because we have to integrate it. We're going to do that next. Doesn't wind up being quadratic. If it's me taking notes, I highlight or put a box around that part that's in red. I made it in red to make it stand out. That's a big, big deal. There's three different orders that we're going to have to worry about. There's first order, second order, and then there's actually zero order. And zero order is not something to make fun of, but we're going to see mathematically zero order will make sense. Unlike the zero with law, which is dumb to me, zero order will make sense. Good on this one? All right, there's an example in the book. I want to come back to this in a moment. I'll show you the example after we have a chance to look at a different order so we can see how orders are different from each other. So let's say we have a different reaction. This one winds up being a second order reaction. A yields B is second order in A. Don't get frustrated if you have no idea what order means. We haven't really learned it yet. We will. And the order is going to make a big difference as to how the reaction is going to proceed. But we're not there yet. If it's a second order reaction, that means that the differential rate law, which is right here,